In this module, we will get acquainted with a powerful quantum communication operation, whereby two parties that are not connected directly are able to establish entanglement by consuming a Bell pair and two classical bits. This fantastic quantum communications primitive, impossible with classical communications, is called entanglement swapping, or teleportation of entanglement. In this primitive, we have two parties, blue and yellow, which would like to share a two-partite entangled state, such as a Bell state. Since blue and yellow are not directly connected, they will both prepare entangled states inside their own labs. They will then keep one of the parties of their entangled state and send the other to a common intermediate station presented by purple, where a Bell state projection measurement will be performed. In possession of the results of this measurement, blue and yellow will be able to share an entangled state after a unitary operation is performed. In order to grasp how this is possible, we will introduce the means to create a Bell state and to analyze a Bell state, the latter being performed through a so-called Bell state analyzer. A Bell state analyzer, analogous to a qubit analyzer, allows one to determine which of the four Bell states are encoded into a two-party system. Since the Bell states form a basis for any two-partite quantum state, the Bell state analyzer performs a projection onto the Bell basis. Let's start by reviewing the Bell states and how to create them. As you will remember, there are four maximally entangled two-partite states, which are called the Bell states. One important feature of the creation of these Bell states is the presence of the C0 gate after the application of the Hadamard gate on the upper qubit, which has the effect of entangling the two states. It is also interesting to note that it's possible to go from one Bell state to any other through the application of a unitary operation. Consider now that an arbitrary Bell state has been created, and we would like to determine which of the four it was. It is possible to do that by projecting the input Bell state onto the computational basis. This leads to a very distinct pattern of the results of subsequent measurements in the Z basis. Therefore, by matching the resulting pattern with the expected pattern for each Bell state, yields the projection result, thus composing the Bell state analyzer. Now, we have the tools to allow entanglement swapping to take place. In the initialization step, the two non-connected parties, blue and yellow, generate Bell states. They keep one of the particles of their respective Bell state and send the other to purple, a common intermediate station. Purple is responsible for running the Bell state analyzer. After the measurement, purple has access to the projection of the joint state of two particles that never interacted before onto the Bell basis. This is important because purple gains no information whatsoever about the states that blue and yellow possess. Purple then transmits the result of the measurements to yellow. The result, encoded into 2 bits, can be used to select which unitary transformation will be performed on the particle of the initial Bell state that yellow kept in the beginning. After this operation, the joint state of the particles in possession of blue and yellow will be entangled. It becomes clearer when we follow the mathematical steps. Let's do that. First, the full joint state can be written. After that, we can apply the following identities. Although the expression becomes quite large, it can be easily simplified to reveal that, conditioned on the result of the Bell state measurement in purple's Bell state analyzer, the joint state of blue and yellow will be projected onto one of the 4 Bell states. transforming one Bell state to any other Bell state is a unitary transformation away, which is given by the result of the BSM. This concludes this marvelous protocol called entanglement swapping.